Okay, so today is a very exciting video for me because usually what I'm doing, I'm talking about, teaching FRNs and teaching undergrads and teaching fixed income guys. But what I'm going to do tonight, what I'm going to do today, I'm going to talk about my own research. Okay, so it's a little bit unusual, but we'll see how it goes. So I'll talk about it, I'll put it on my channel, and I'll see if people actually relate to it in any shape or form, okay? So what I'm going to talk about is a joint work with Bernatska from Mohilanka in Ukraine and Tony Shaska from Auckland University in Michigan. And what I'm going to talk about is addition of divisor or reduction of divisor on hyper-elliptic curves. So I'm not going to introduce the entire shebang in this video because it will take too much time. Okay, so I will assume that you guys know something about, about the theory of Jacobians and elliptic curves and all that stuff. So basically, we talk about, so basically an elliptic curve is given by this equation, and if the degree if the degree of this curve, if the genus of this curve is g, we know that the degree of fx will be 2g plus 1. Okay, and we also like to know, okay, that infinity is a ramification point. So now, introducing the Mumford standard notation, the a divisor d of degree 0 inside G Jacobian is called reduced if we can present it in the following form: d prime minus g times infinity, and d prime is a positive divisor of degree g. And those divisors of this form are called reduced divisors. Now, these guys, okay, so if you look at the Jacobian, you mod it by the symmetric group. If you look at the symmetric product of the curve g times, you mod it by symmetric group. These guys form a fundamental domain, okay, of the action of the symmetric group on the Jacobian, on the xg, okay? So the reduction problem is, say you have a divisor, d1, which is given by the following form. It's like a divisor d2 minus g times infinity, and the degree of d2 now is greater or equals than g plus 1. Okay? So what you want to do, by Riemann-Roch, okay, or by that you can actually take d1 and you reduce it to d. So basically, the reduction problem is to find a divisor, find a reduced divisor which is equivalent to d2 in the Jacobian. Now, there is, of course, a very famous work by Cantor, David Cantor, from '87, when he solves this problem. He solves this problem. So there is already an algorithm. Okay? I'm not going to explain in this video the ramifications and the details of the Cantor's algorithm because it's a very well-established algorithm. And it's used, it's used somewhat. Now, for small genuses, genus 2 and 3, though we have direct solution of the reduction problem. So given d2, we know exactly how d prime is going to look like. This was done for genus 2 and 3 because of cryptographic applications. And And we will talk about cryptographic applications maybe some other time. Why hyperelliptic curves are interesting in cryptography. I'm not going to go into that right now. Okay. Now, what I'm going to do, I'm not going to present Cantor's algorithm. I'm going to present another algorithm, which I didn't see appearing in the literature. And this was done, and this algorithm was inspired by my joint work with Tony Shaska. We have a paper, but where we did something for the superelliptic curves, but we didn't do what I'm going to present now there, but it's kind of a simple consequence. If you want, I wouldn't say a very simple, but a simple consequence of this. And from, from Julia, that actually kind of inspired me to do it, because she actually asked me a couple of questions which led to what I'm going to present now. Okay? Now, if you want to approach, now, if you have D2, where of this form, how do you want to reduce? So of course, okay, so you have the Cantor's algorithm, but let's say that you don't know Cantor's algorithm, so how can you think about this problem? Okay? So let's say that you have G plus 1 points. Let's say that you solve the problem for G plus 1 points. Now, I observe that if you solve the problem for G plus 1 points, so if you have D2, such the degree of D2 equals to G plus 1, and you know how to do it for this degree D2 G plus 1, I claim that you're done. Why are you done? Because let's say that you have D2, D3, which has, let's say, G plus 4 points. So how do you do that? Okay, so you take your first G plus 1 points, right? You reduce it to G. And then here you have another 3 points. So basically you take G plus 1, you reduce it to G, you have another G points. Okay, so now you add another point to it, and you have G plus 1 points, you reduce it again, and now you have another point to G plus 1, and you reduce it again, and you are actually done. That's it. Because you started with G plus 4, and successively, by adding those points one by one and reducing them one by one, you get it to a reduced divisor of degree G. Right? So here you have G plus 1. You reduce it, you get G. You add another point, you have G plus 1. You reduce it, you have G. You get another point, you have G plus 1. You reduce it, you get G. Okay? Now, how do you actually approach it? Okay, now, so now what we want to do, so basically it's a recursive algorithm. Now, if you know how to do it for G plus 1, it's a recursive algorithm, but then there is going to be an objection. You don't know what you're talking about, because if you have G plus 1 points and you reduce it to G, and then you add another point, you need to know your G points of the reduced, right? So if you have G plus 1, then you reduce it to G. So let's say this is x1, xg plus 1, y1, yg plus 1. And now you reduce it to x1 tilde, y1 tilde, x2 tilde, y2 tilde, yada, 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 xg tilde, yg tilde. It seems like you need to know those points to continue, right? So what have we accomplished? Every time we need to kind of solve this, we need to kind of to find those points. So it's actually very cumbersome. But this is an illusion, and this is kind of the observation of this video, and I'm going to show you why this is an illusion. Okay? So let's just remove some of the stuff so that we can write, and I'm going to show you this neat trick so that you'll be able to see what I'm going. So, conceptually what I'm going to present now seems to me a little bit simpler than what Cantor did. So maybe you can use it, in your classes as kind of, or maybe to implement it, because it's implementable, and I'm going to talk about it in a moment. So maybe you'll be able to talk about it in your class. I don't know. I mean, I just like it so much that I kind of decided to present it like this. You can't argue about taste, can you? Okay, so now let's go back to our stuff. Enough with the blah blah. Let's go back to our stuff. Okay, so what you have here, you have a divisor of degree D2, and let's say that this is a degree D2 prime minus g plus I times infinity. Okay, now what you want to do, you want to reduce this divisor. You want to reduce this divisor. So we said, okay, first let's look let's see if we can reduce a g plus 1 divisor. That's the first thing we want to do. So now what we're doing, we're actually starting as we did, what Cantor did. So what Cantor did, he actually said, okay, if I have a D2 like this, let's say that I have g plus 1 points, where I have x1, y1, x2, y2, yada, 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 xg plus 1, yg plus 1, I'm going to first do an interpolation polynomial through this point. So I'm going to have basically p, which is my interpolation polynomial. So this will be a unique polynomial of degree g, such that I of xi equals to yi. OK? So that's the first step. Now, on the first stage, it is actually very easy to find the resulting, okay, and to find the resulting polynomial. Why? Because when you have interpolation polynomial like this, if this is your interpolation polynomial, it kind of intersects the curve, which is given by y squared equals to f of x. Okay? How many points it will intersect the curve? Now, because the degree here of x is 2, okay, it is easy to see that if you have a g plus 1 polynomial of this form, okay, he will the pole at infinity has a 2g points, right? So you have g plus 1, and then you have 2g plus 1. The pole has a 2g plus 1. The order of this polynomial at infinity is going to be 2g plus 1, and hence you have g points of intersection with a curve. Okay? So let's say that those points are x1 tilde, y1 tilde, xg tilde, yg tilde. Now, how can you find them? Well, it's actually very easy. You take this interpolation polynomial and you substitute instead of y, because in this case, the interpolation polynomial is just a Lagrange interpolation polynomial, no problem at all. You substitute it instead of y. So you are getting basically, because this is a polynomial of degree g, here you are going to get a 2g guy, right? So you are going to have an equation in x. And this equation has, you know that it has already 2g plus 1 roots, the roots that you started with, because you know that xi, yi, I goes from 1 to g plus 1 belongs to the curve. Okay? So now you have another g points, and these g points will be basically the roots of the polynomial I of x squared minus f of x. And you can divide. You know that you can divide. And when you divide, and we will talk about division in a moment, but when you divide, you're getting a polynomial of degree g. Okay? And the roots of this polynomial are going to be the additional g intersection points that you see for this intersection, for this interpolation polynomial with this curve, which is given by this. Okay? So the quotient of this guy versus x minus x1 times x minus x2, yada, 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 x minus xg plus 1, is exactly the polynomial that you are looking for, which has a correct degree, that it will have g points. It will have g additional roots. Now, what's going to happen that when you are going to take these g additional roots and you are going to substitute instead of these p's, okay, inside this guy, you're going to get exactly, okay, the new yi's. That's it. Okay? So, you're having basically from here, if you know the roots, x1 tilde to xg tilde, you can substitute them and you can get the x1 y1 tilde until yg tilde, something like that. Okay, now there is a small problem here. The problem is that a priori it looks like that in order for me to get those kind of result, I need to know exactly what x1 to xg tilde and y1 to yg tilde is. And that's where it is not, where it is just a mirage. Because it turns out, amazingly, that you do not need to know the x1 tilde to xg tilde in order to get. Now, here, right, you start with an interpolation polynomial. And here's the interpolation polynomials of degree g. Now, if you want to get the pure polynomial, which is corresponding to the data x1 tilde, y1 tilde, xg tilde, yg tilde, and note that if you have an interpolation polynomial that goes through these points, then you characterize these xi's and yy's uniquely because because of the uniqueness of the theorem of the interpolation polynomial. In other words, if you have here an interpolation polynomial of degree g minus 1, you can actually basically forget about the points themselves and just look on the interpolation polynomial of degree g, as long as you know what is x1 minus x1 tilde, x minus x2 tilde, x minus xg tilde. So in other words, if you start with ix, where you have where it corresponds to g plus 1 points, and you start with x minus x1, yada yada yada, x minus xg plus 1, which corresponds to to the g plus 1 points. Let's say that this is, let's call it polynomial px. Now, if from this pair you can get the pair which corresponds to x1 tilde, xg tilde, where you have this p, which is going to be p tilde x, okay, and where you are going to have I tilde x, okay, then you're basically done. You're basically done. You don't need anything else, because those guys, this pair is going to correspond exactly to the pair of x1 tilde, y1 tilde, x2 tilde, y2 tilde, yada yada yada, xg tilde, yg tilde, uniquely. Why? Because the roots of p tilde x are going to give you the xi's, okay, and then when you substitute xi's, you're going to get, into this, you're going to get the yi's, okay, and this I tilde is unique. So now, okay, it looks now, this is a very, very important conclusion. What you want to do now is to see whether from this px that you have with these g plus 1 points and ix, you can somehow cook the polynomial that corresponds to p tilde x and I tilde x. Now, p tilde x is easy, because p tilde x is exactly going to be, p tilde x is going exactly to be what we want. What we want is I x square minus f of x, and then you divide by the product of x minus xi, I goes from 1 to g plus 1. So you're done here. What about the other one? Well, that's where it gets interesting. So what you want to do now, you want to define I tilde x. How do you define I tilde x? And that's the main idea here. You can define I tilde x as ix minus I0, and I'm going to explain why what I0 is. And this is going to be x minus 1 tilde times x minus xg tilde. And maybe we should divide by something. We will see. We will see now, OK? Now, why does it work? Because observe. Because observe. OK? I claim that I tilde says that I claim that I tilde x is a correct degree, provided that here this x minus x1 tilde x minus xg tilde, we will take I0 to be the major coefficient. The major coefficients of ix. So if ix, I can say that it's a0, I0, xg plus 1, xg plus yada yada, ig plus 1 or ig, whatever. Okay, I'm going to kill this power. That's the idea. I want to use these guys in order to kill the power here. Okay, and how does it work now? Well, if I'm going to substitute xi tilde into I tilde xi tilde, okay, ixi is going to give me the correct yi's. It's not going to give me, it's not going to be the correct yi's, it's going to be minus yi tilde, but you know, because when I look on the curve and I add these g guys, they will be, the sum will be 0. Okay, the sum of them will be 0. So I want to make a slight modification to I tilde x, but we will talk about this in a moment. So it's ix here. When I'm going to substitute xi tilde here, I'm going to get yi tilde, but here I'm getting 0. Because the roots of this polynomial are exactly what I need. Now this guy is exactly p tilde x. I'm done. That's it. So I can produce I tilde x and p tilde x without knowing the roots of x1 tilde xg tilde. That's it, right? So I actually did this reduction from g plus 1 to g. The first step. I'm done. I'm actually done. This is like, I don't need to calculate any roots. What I'm doing, I'm actually, instead of working with the Jacobian with the divisors, I'm working what Tony was talking about as a geometric model of the Jacobian. Okay? And the geometric model of the Jacobian is given by these curves. In this case, in a general case, it will be somewhat little different, but the idea will be the same. Okay? Now, if I have now the only piece of the puzzle that is remaining, okay, the question is, okay, you got I tilde x and you got p tilde x. What will be the next step? How can you calculate this I tilde? Okay, now, let's say that you add another point, because we have g points here, and you add another point, and now you have g plus 1 points. And the question is whether you can calculate from this guy, you can calculate this g plus 1 tilde, yes or no. Okay? So very simple. Okay, so now you have I tilde x, which corresponds to these new points x1 tilde to xg tilde. And then you have p tilde x, where it corresponds to these new points x1 tilde xg tilde. And we know that p tilde x equals to x minus x1 tilde x minus x2 tilde, yada, 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 x minus xg tilde. So now you add another point because you want to continue this recursive process. Okay? And what do you do now? Well, you have this p tilde of these new points just defined. So let's say you're adding a point x. Let's say, I don't know. I mean, I'm running out of letters. Let's say x tilde g plus 1, y tilde g plus 1. So let's say you have a g plus 1 divisor, and now you have a g plus 2 divisor, okay? And you want to take the g plus 2, so you calculated the g plus 1, you calculated r tilde p tilde, and now you want to go and to calculate this for g plus 2. So what do you get here? Okay, so p tilde x, the new one, is going to be no more, no less than what? It is going to be just, well, x minus x1 tilde, x minus xg tilde, times x minus xg plus 1 tilde. I'm just adding these points. That's it. That's all I'm doing. Now, what about I tilde x? Well, same story. Okay? It's the same story, right? So what I'm going to do now, I'm going to define a new polynomial, I1 tilde x. And now this I1 tilde x, let me see if I can, maybe this. OK, great. So I1 tilde x is going to correspond to the point, x1 tilde y1 tilde, x2 tilde, y2 tilde, xg plus 1 tilde, yg plus 1 tilde. And remember, this is the point that I want to add. So I have the polynomial which corresponds to these guys. And what I want to do, I want just to add another one. So how do I define this I1 tilde from I tilde x? OK? It's actually easy peasy. So I'm taking this I tilde x that I have. OK? And I'm going to add or subtract, probably subtract, I tilde at a point of xg plus 1 tilde. I don't know what this point is, so I'm going to subtract it. I'm going to add the value yg tilde plus 1. And now I'm going to multiply it by, well, you may be guessing, x minus x1 tilde, x minus x2 tilde, yada, 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 x minus xg tilde. And you know, I know this guy, right? No problem. Divided by x tilde, xg plus 1 tilde minus x1 tilde, xg plus 1 tilde minus x2 tilde, blah, 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 blah. And I'm done. That's it. Because if I'm going to substitute any one of these xi's, I'm going to get this value because here it's going to be 0. Bang. So I'm getting exactly yg tilde because by definition of this. Now, if I'm going to multiply to substitute this guy is going to basically cancel with this guy because this guy will be 0. Well, not 0, sorry, 1, right? Because if I substitute this, now here, know that I substitute this guy into the polynomial p tilde x. So no problem. This I can rewrite as p tilde x tilde g plus 1, and I'm done. So what I do now, I'm getting my new I tilde x, I'm getting my p tilde x, my p, which corresponds to g plus 1, and then I'm doing exactly what I did before. I'm taking this new I tilde, I'm plugging into the equation that I had before, ix minus ix squared minus f of x. And I'm going to divide by my p tilde x, because it is divisible. So, because these guys are intersections. So I'm done. OK? So I can actually now successively reduce it. And at the end of the day, after, let's say, I have 10 times I'm reducing, I'm getting I tilde reduced and p tilde reduced. That corresponds to the entire divisor. Now, each one of them, right? The roots of this guy will be exactly my xg tilde, and the roots, and then if I substitute here, I'm going to get the y's. Okay? Now, what about division? How fast this division is? Well, the answer is very fast. If you willing to use the fast Fourier transform, okay, you can do this division. If you have degree n, you can do this division in this form. N log n, right? So to implement it, it's actually very fast. And to do this kind of simulations, kind of substitution is very straightforward. Now, the question is, okay, why are you telling us this? Why didn't you implement it yourself and have a software? Okay, so my answer to that, okay, is that I did not implement it myself because I can implement it only numerically. I do not have a software that does a formal division, let's say square root of 2 divided by square root of 3, which is what we want to do if you want to implement it. Okay, but this seems to me easier than what Cantor did. I'm not saying that it's actually better. I'm just saying that it's easier. And as a teacher, if you want to explain the reduction algorithm, this I think is much easier than Cantor's algorithm. Okay? Now, the important fashion of this algorithm, that it actually can be, I'm claiming that it can be actually generalized to any curve. Okay? But we will talk about this in another video. This is being written by us now, and we're going to post it on the archive. So we're going to post this thing on the archive in the following week. And under the video, I'm going to assign a link to the archive paper that you guys will be able to see a more formalized. Okay? So I wish you happy holidays, and I do thank my co-authors, Julia and Tony, for this wonderful result. I'm really excited about that, but it is just me. I like those tricks. All right? So have a great day. Bye.